And okay, there's still more rotaries needed. Housings. Like I said, I'm not using these. I'm going to be using the T motor, 36 kilograms thrust, and I'm going to be using small rotary frames. These are going to be, it's going to be smaller than what's fitting in this housing. I use this housing because it's in minimum size of my biometric range or area of the of this orthosis. And I have to add the servos connected to the fan bracket. It's going to be 4 servos a piece per unit, but actually additionally on the corner, on the external linkage to the other parts, which this makes incorporates one leg. The linkage between servo to servo, it should enumerate about 16, about 24 servos, and 24 60 kilogram servos for now, using a minimum size, 60 kilograms. There is also vacuums that will be added. There's 4 vacuums, 2 on each part of the foot. Notice how the foots are separate together, and when it closes, it would close both of the feet together under the feet. Housing 2 vacuum dispatchment fans underneath the foot, about 100,000 RPMs per unit. There'll be enumerated 4 in 2 in each shoe, 4 altogether. There's another fan that has to be added here, which is going to be similar to the adductor fan for the hip. Behind the bracket, the rotary bracket of the hip, will be the hub. The hub will torque these segments for ROM, for legging, walking, ROM. And for the attachment, the couple to that linkage is the servo motor. If that is linked into another hub in series for horse, biaxial, and also for ROM, for painting, for splitting in robotics. Now, the linkage between these, which is similar to a guider, whereas there's 2 parts, one electromotive will be solenoid, where each one of the plastics will be wrapped in winding coil. So then overlaid with the epoxy resin crystal liner hardener, which will protect the coating of the magnetic wire. And that will be used to bring an electromagnetism to a whole in likenesses of motor stator, whereas have 4 terminals, Hall effect terminals, in a vertical position. However, these being in a vertical position, we're able to push the vertical position like a solenoid functionality. So, using the scissorine, 2 scissorines coupled together, one on top of another, which allows it to guide and to swing. The linkages of the ends between the scissorine will be connected to the hub, which will be the biaxial for the knee. And in series, the connections local to it will be connected to it will be the scissorine. So the scissorine armature bracketed to the motor bracket, so that it would torque the scissorine for turning Biaxial Rom, which connects the linkage between the linkage. Now, under here for the scissorine for drawing sliding, which will be behind the knee, whereas the knee will push 2 of these linkage together, coupled to a latch, will allow it to fold out and to move. Thus, it could swing over in different directions, so that it may turn from on top of one another into release and to stretch in distance and sizes of the scissorine. So, by an actuator stepper motor actuator that'll pull the scissor rings together or apart to cause it to slide. Now the servo, which we mounted to this bracket, will move this part for tilting left and right, while the screw rod stepper motor is mounted in a permanent state to this arm, so it allows it to pan up and down. So the whole effect is to cause it to move like an actuator. Nickel neodymium block magnets will be localized within the segments, so that the solenoid would not only push the coil but also push the electromagnetism. Even though the rotary, the housing is magnetic, it can be magnetized, and having nickel neodymium within the plastic, so I'm gonna have it embedded within the interface. This will enable it to move like a solenoid, a rod that goes up and down out of a winding coil shaft. It'll launch force linear motion. Anyway, so that is next, and see you later. My name is Jermaine Warren. I'm out.